Yeah, I'm starting to do a recording, and then I can do a share screen. Yes, it is. Okay. So after discussing Dirac, and last time we had this tutorial about isospin symmetry, the flavor, and I introduced you the CKM matrix, and the Cabibbo angle, and the Jim mechanism. Now I'm going to do somewhat relaxing, I think. Maybe not. We're going to do gauge theories. Well, introduction to gauge theories, QED and QCD. What I'm really going to do now, I'm going to give you some basic fundamentals of quantum field theory. So it's there is some overlap with the basic first two lectures of quantum field theory. So that will help you to understand the logic of what's going on here. And I think it's a good intro to have this in mind, you know, before you actually go and learn it, because these things can be very confusing at first. Okay, so, you know, in classical mechanics, if you speak about classical mechanics, that's what you're used to and love, right? And what we're interested in is to look at the motion of particles, right? Basically the trajectory. What do we mean by the trajectory of a particle? We mean the time-dependent location, right? Trajectory of a particle, meaning a time-dependent location. And we do that by solving, you know, the differential equation, which follows from the kinematics of the problem, right? Essentially, the differential equation is Newton's second law of motion, right? F is m x dot dot, right? And that gives us the trajectory. Now, the next step that you're supposed to learn, I assume, right, is a quantum mechanics, right? Quantum mechanics. Right? So in quantum mechanics, right, we treat a particle not as a point-like billiard ball, but as a wave function, right? Of a wave function. But the wave function itself obeys a differential equation, which again follows from the kinematics, right? But here also, it can also be the spin, right? This could be the Maxwell's equation, can be Dirac equation. Of course, in the classical non-relativistic quantum mechanics, when I say classical quantum mechanics, what I really mean is non-relativistic, this would be Schrodinger's equation, right? Wave function that follows wave function, which obeys the differential equation. Right? Now, in the framework of quantum mechanics, of course, the probability of finding a particle somewhere, right, is always unity, right? Probability of finding a particle is 1, right? And the particle nature, right, of the wave function is only manifested when this wave function interacts with a macroscopic system, right? That is the measuring device, essentially, right? We treat the particle as a wave function until we make a measurement. When we make a measurement, then we know that the wave function collapses, and then we say this is a, you know, discrete particle, right? But only then, right? So the particle, like the nature of this particle nature of the wave function is manifested when interacting with a macroscopic system, right? The measuring device is always something macroscopic. QFT is somewhat different than both of those. So quantum field theory, QFT, the basic entity is a field, okay? It's not a particle, it's not a wave function, it's a field. And a field also fulfills a differential equation, right? Let me write it down. The basic entity is a field, right? Which fulfills very similar. It feels similar differential equation. Then what is a particle? I mean, we know there are these things which are called particles. So what are particles in the framework of quantum field theory? Any suggestion?
Can you repeat?
What?
Repeat the question?
What are particles? If I'm talking about fields, then what would be particles in this framework? How do I get from a field to a particle?
Field is a charge that moves. Well, no, it's a...
No, it's a field, right? A field. Think of an electric field. It's there everywhere. Okay, it's a tricky question because it requires some, you know, non-trivial lap, really. The field, a particle is an excitation of the field. Okay? It's a quantum field theory. It's not classical. So the fields are quantized. And then every time I quantize a field, right, I excite the field, right? It can be in the ground state. It can be in an excited state. Every excited state of the field is a particle, right? A particle is described as excitation of the field. Now it's a different concept, really, right? I mean, it's not a classical thing. I mean, you can think of a field in terms of a sea, right? You have an electric field, a temperature. Here it's quantum field, right? So fields are quantized, and then every time you excite anytime you're exciting a field, this is end up as a particle. The field itself is treated as a quantum operator, so it can create and destroy particles, right? In fact, the way it is being worked out mathematically is very, very similar to the ladder operators that you learn about in quantum mechanics when you treat the simple harmonic oscillator, right? I assume you all learned that in quantum mechanics, right? The simple harmonic oscillator and the ladder rising and lowering operator. It's identical in mathematical structure, right? But in the framework of quantum field theory, when you're exciting, you can create a particle or you can destroy a particle if it goes down, right? So the field, let me write it down. The field is a quantum operator that creates and destroys particle in an analog way to the ladder operator. In the simple harmonic oscillator. Now, interaction between particles, remember quantum field theory, we can have interactions, right? It's described by multiplicity of such operators. So we can have two operators that you multiply them and one of them destroy a particle and the other one creates another particle. The visualization is of course a Feynman diagram. The interaction. The vertex in the Feynman diagram is exactly the location where you have one field which is going down and one is excited. So you have one particle is created, one is destroyed. Interaction between particles is described by multiplicity of operators. Right. Destroying some particles while creating others. So quantum field theory, as opposed to classical or non-relativistic quantum mechanics, quantum field theory does describe the dynamics which enable particles to be created and destroyed. Right, so particle number is not conserved, but as opposed to non-relativistic quantum mechanics, where Schrodinger's equation does not allow the destruction of a particle or the creation of new ones. Right. A classical example of the electromagnetic field. Right. So an electromagnetic field, if there are no photons, we say that the field is in the ground state. Right. The first excited state corresponds to a single photon, which has a well-defined momentum. The second excited states would say that there are two photons, etc. Okay. State, no photons. First excited state means like one photon. The second excited state, two photons, etc. Now, I said that at the beginning of the course, if you remember. Within quantum field theory, we said that a model is described by the Lagrangian, which holds which I can this one, yeah, okay. So within the framework of quantum field theory, a model is described by the Lagrangian, right? A model is described by a Lagrangian. And the Lagrangian holds all the information about two things. One is what are the particles involved, right? I gave you an example in one of the tutorials of particles A, B, and C. And the second thing, it's not, what is the second thing? You write the first one and while you think on the second one, the Lagrangian holds all the information about one, what are the particles? Right? And can you hear me?
Yes.
Okay, good, because I wasn't sure. Okay. What are the particles? And the second one is what are the symmetries? All the symmetries are derived from the allowed terms in the Lagrangian, in particular the interaction. Okay, I'm going to explain to you in a few minutes what it means exactly. Now, the most general Lagrangian describes the entire known physics. So we put the whole known physics into one big Lagrangian. Okay, this is including all the standard model and all the new physics, the beyond the standard model additions, right? But of course, fortunately, we don't really need all that because we nearly always work only with one part of the Lagrangian, the part that is of interest to us. And we don't care about the rest. Okay? So the most general Lagrangian will become clear in a few minutes, I hope. The most general Lagrangian describes the entire known physics. All the standard model plus the new physics. It's quite cool. In fact, you know, Feynman rules, right? We discuss Feynman rules, we learn about them. Which, you know, we learn how to write them from given Feynman diagram. We can derive them from the Lagrangian. And once we know the Lagrangian will tell us how to derive the Feynman rules, right? And the Feynman rules, they tell us how to calculate the quantum probabilities, right? The cross-section and the decay width and the branching ratio, right? So just Feynman rules are derived from the Lagrangian. And from Feynman rules, we got, from Feynman rules, we got the cross-section, we got the decay, right, gamma, decay weights, and the branching ratio, which will tell us for a given particle to which particles it would decay, right? So obviously this is something which is experimentally observed, and then we can validate the model and explore the allow parameters. All right. Now, okay, we're not going to do the full development, obviously, but to get the basic language, we will do a short review on Lagrangians, and I will introduce to you, you know, the basic Lagrangians of QED and the QCD, and especially emphasize on these ideas of symmetry of the Lagrangian and how these manifest themselves in nature, like in the non-particles in nature. All right. Is that clear? Questions? No. Okay, so let's start with something which is simple. This is Lagrangians in quantum mechanics. Just as a reminder, or sorry, in classical mechanics. Lagrangians in classical mechanics. This is something which you've seen already, right? Is there anybody who did not see Lagrangians? No, right? You all seen the Lagrangians. So just as a quick reminder, right? The equation of motion of a particle is described in terms of the forces and the acceleration. We can use Newton's second law, F equal mx dot dot. But we can get the same equation, right? This is Newton's law. Well, we can get the same equation by the Lagrangian. So we define the Lagrangian as T minus V. T is the kinetic energy. V is your potential energy of the system, right? The Lagrangian L, this is a scalar, right? Which is a function of what's known as the generalized coordinates. So these can be the regular coordinates we use, but this can be other things as well, right? So it is a function of the generalized coordinate and their derivatives. L is a scalar function. The scalar function of the generalized coordinates Qi and their derivatives Q dot I, right? Now I explicitly assume that there is no time dependent in the Lagrangian. Once we specify the Lagrangian, then the equation of motion is the Euler Lagrange equation. This is what replaces Newton's second law. Or simply write equation of motion. Right? d over dt of partial derivative of L with respect to Qi dot minus dl over dqi, no dot, is equal to 0. Right? This is the Euler Lagrange equation. I'm not telling you any news here, right? You've all seen that, so you know what I'm talking about. Now this can be derived also from what's known as the principle of least action. And another name for that is the Hamilton principle. Right? Which, using the quantity which is known as the action, S is integral from T1 to T2 of L dt, right? And the principle of least action states that delta S, a small variation in S, right? As we, taking the integral path from, the location of the particle at T1 to location at T2, then it has to be minimum. So when we take a delta of T1, T2, L dt, needs to be equal to 0, right? So delta S, this is a small change in action. Meaning that the action needs to be in a minimum, right? Now the proof of that is quite straightforward, right? So if we switch the order of the integral and derivative, so switch order, and we get that integral from T1 to T2 of delta L dt is equal to 0, right? And delta L is a variation of L, but L is a function of the coordinates. So delta L, Qi and Q dot I, right, is just dl over dqi delta qi plus dl over dqi dot delta qi dot. That's the only possible variation of delta L, unless L is depending on time directly, which is not. And what we're left is to integrate by part and use the fact that the change in the coordinate delta qi must be 0 at the boundary. So integrate by part. And use delta qi at t equal to t1 is equal to delta qi at t equal to t2 is equal to 0. Then automatically you get delta s is integral from t1 to t2 of dl over dqi minus d over dt dl over dqi dot delta qi dt is equal to 0. Right? So using that, automatically you get the Euler Lagrange equation. Right? This is equal to 0. You've seen that, right? I'm not telling you anything new. No news. The reason why I do that is because I'm going to do it in a second for quantum fields, and that's going to be slightly different, but very similar. So that just to refresh your memory. Now, specific example, right? So just as an example. By the way, is there anybody who's any question about that? No, it's okay. So everybody, raise your hand, say something. Yeah. Whatever, right? So let's say we have a particle moving in one-dimensional, 1D motion, with the Lagrangian is a function of the coordinates and the derivative. So let's write down that L is t minus v is 1/2 m x dot squared minus v of x. Then of course dl over the x dot. What is dl over the x dot? What is dl over the x dot?
mx dot.
Mx dot. Right, what is dl over dx?
Derivative of vx minus vx.
Right. So the Euler Lagrange equation, right, it's just m x dot dot is minus dvx over dx, which is exactly Newton's law. Right. I didn't tell you anything which you did not know already. All right, let's take another Lagrangian. Right, if we have a Lagrangian of the form, now we have a two bodies, right? So 1/2 m q1 dot squared plus 1/2 m q2 dot squared minus v12 of x1 and x2, right? So this Lagrangian would give us via the Euler Lagrange equation, right, a two-body system, right, which interact with each other via a potential that depends on the location, right? So for example, this is a two-body system interacting with each other. Right. And V can be, Coulomb, for example. Is it V1 and 2, x1, x2. It's just q1, q2 over x1 minus x2. Sorry for that. So again, kinetic term and interaction term. Now let's go on to QFT. It actually should be x1 here. Okay, pay attention here. I think I made a typo. Okay, Lagrangians in QFT. So the big difference is there are several subtle points here. So the first point to note, right, in classical mechanics, right, the Lagrangian is a function of a discrete number of coordinates, right? I mark them as Qi, right? Normally it could be X, Y, and Z, I of each individual particle. But in quantum field theory, the basic entity is not a particle, but is a field, right? And the field is defined everywhere, right? And it's a continuous function at every point, right? Again, think of an electric field, right? Which is defined everywhere. It's not just as a single point, right? And when we speak about the energy, let's say, kinetic energy or potential energy, we're looking at the energy of the field, not of the particle, right? Which is, again, it's something which is continuously defined everywhere. Okay? You need to, it's a bit subtle, so that's why I'm emphasizing it. So in classical mechanics, right, the Lagrangian is a function of a discrete number of generalized coordinate. Right? Qi, xi, yi, and zi. Specific example. Right? In QFT, it's not a particle, it's a field, so it must have a continuous. Now in QFT, we have continuous fields. Right? And all of them have infinite number of degrees of freedom, right? Because we have at least 1 degree of freedom, the value of the field in each location, right? So with infinite number of degrees of freedom. Right? And this is what replaces the generalized coordinates. So as opposed to the classical or even quantum mechanics, right? In quantum field theory, the dynamical degrees of freedom are the values of the field at every point. You write it down because this is the key point, which can be quite confusing. As opposed to classical mechanics, classical quantum mechanics, right? In quantum field theory, the dynamical degrees of freedom are the values of the field traditionally you call it phi or psi. There can be many fields, right? Or E or B or whatever you want, right? At every point. So since we want to incorporate this idea inside the Lagrangian formalism, we need to extend the Lagrangian to continuous systems. Right? So I have to extend the Lagrangian to continuous systems. Right? And the way we do it is to introduce what's called the Lagrangian density. So we introduce the Lagrangian density. Shouldn't be really worried about that. It's abstract, but it's not different than number density or energy density. The number of particles per unit volume. The total energy that is stored in the system per unit volume. So here we have a Lagrangian density, which is denoted by curly L, like that, which by itself is a function of the field and also the derivative of the field. And of course, another change is now we're looking not only at the time derivative of the field, but also on the spatial derivative of the field, right? Which is a function of the field. Let's call it phi, and its derivatives, right? Time and space. So this change is from L, which is a function of Qi and dQi over dt, to Lagrangian density, which is a function of the field phi and d mu phi. Right? There are several changes that I made here, right? Pay attention to all of them. Now the field is continuous, right? These are continuous functions of the space-time. So, so at every point x mu, we can think of full Lagrangian, right? At every point in space-time, or not at every point, it's not an appropriate term. Let's say the fields are continuous functions of space and time. So we can always define the Lagrangian by integrating over the Lagrangian density. Integral over L over space, right? So you take a volume element and you integrate the Lagrangian density and you get the Lagrangian. And if you want to get the action, right, it's integral from T1 to T2 dt, integral L dqx. So it's really integral over L over the 4 coordinates. Okay, so we have integral, this is the 4 volume basically, right? So we can, by doing that, we can generalize the concept of the action to, the framework of the relativistic theory. This is generalizing the action to a relativistic theory. Now we can look at the principle of least action, right? So let's apply the principle of least action. Right? And what we're going to get is a relativistic analog to the Euler Lagrange equation. So 0 is delta S, that's the principle, right? So this is integral delta L Lagrangian density B for X. So again, the Lagrangian density is a function of the field and their derivative. So it's just integral of delta phi I dl over d phi I plus delta d mu phi dl over d mu phi I d to the 4x. And then essentially we just repeat the same calculation that we were doing for the classical Lagrangian. So we first replace the order of differentiation in the second term. So we have delta d mu phi I is d mu of delta phi I. This is just a change of order of differentiation. And then we can take this term and integrate it by part. Integral d mu delta phi I dl over d mu phi I, right, d to the 4x is just delta phi I times dl over d mu phi I and the boundaries of the volume we're integrating minus integral delta phi I d mu dl over d mu phi I d to the 4x. Right, this is the boundary of the 4 volume on which we carry the integration. Right, so this term here cancels out, right, because delta phi I is 0 in the boundary. Right. And we get back from here integral of delta phi I dl over d phi I minus d mu dl over d mu phi I d for x is equal to 0. And delta phi I, of course, is arbitrary. So we must conclude that everything in the bracket has to be 0, which give us the relativistic generalization to the Euler Lagrange equation, dl over d phi I minus d mu dl over d mu phi I is equal to 0. Again, this is the Euler Lagrange. So in fact, if you follow the math, it's pretty much identical to what we do in the classical case. But the conceptual differences that is now we first talk about the Lagrangian density, and then the Lagrangian now is a function of the fields themselves, not of the coordinates. Right, and the fields themselves, they do carry the energy, they do carry everything. And of course, the integration now is over 4 space-time. Right? It's not just time. And the result, of course, is similar. Questions? Let's take a quick example. So, a classical example just to demonstrate the concept of Lagrangian density, right? Not even quantum anything, and even not relativistic. So let's look at a string. So example will be a classical 1D field theory. And the textbook example would be, a string or some rope, which has a mass density. So think of a string of mass density, which is just the mass per unit length, right? Call it rho, and the tension, call it tau. And so I have a string. I have a string here, right? And I am slightly changing the string. So it's a one-dimensional problem. So this is x, right? And then I am now forcing the string to move along the y direction, right? So let's say that the scalar field phi, maybe I was a bit too early in plotting that. So let's say that the scalar field phi of x and t is the transverse displacement, right? Basically, it's the y as a function of x. Right? So it's the displacement of the string from the equilibrium point, which is, of course, a function of both space and time. Right? So it's really y of x and t. Right? So, this is the x, the phi of x and t. Then my string, would be something like that. I have a guitar string, right? Whatever. So I have a mass density rho, and tau is the tension in the string, right? So that means that dt phi, right? What is dt phi of x and t? If you got the idea. What is dt phi? What does it represent? Come on, you cannot be so quiet. What is dt phi? Physically.
The dot.
It's a what?
You mean the symbol or something?
dt phi. I mean, phi. You understand you understand the concept here? I mean, the string you can visualize, right? I'm just saying phi is the the field phi represents the transverse displacement, right? This is phi, right? So what is dt phi?
How it changes over time?
Velocity.
Velocity, thank you. It's simply the velocity. Right? The velocity of the length element, right? So you take the string and we divide it into elements, right? Right. Now tau is the tension, right? So tau d phi x dx phi, what am I doing? Tau dx phi, right, is just tau tangent theta, right? Theta is the angle from the x-axis. Right? This is the returning force. That acts on an element of the string in the y direction. Right? And of course, I assume here that the length of the string is fixed and the string cannot be stretched. So with these definitions, right, we can write down the kinetic and the potential energies of the string, right? So the kinetic energy of the string. What is the kinetic energy of the string? You have to think of a string as a set of, essentially it's an infinite set of particles, right? You think of string elements, right? Each string element is a particle, right? You have infinite of those. Just a way of thinking of it. And that's why I'm going it slowly, because I think it's can be confusing at first, under the assumption that you fully master the Lagrangians formalism. So what is the kinetic energy here?
we need to take an infinitesimal mass element,
right?
half and the velocity squared, and then integrate over everything.
1/2 rho dt phi squared, right? Integrate over what?
Over the string.
So I wrote it down. Right? That will be a kinetic energy. Okay? Very good. We're very good. Okay, it's just a continuation, right? You're making it, you know, again, if you think of it as, you know, n particles attached, and then n goes, and then you take the limit, n goes to infinity, the sum becomes into an integral. This is exactly what it is, right? Kind of help you visualize it. And what will be the potential energy? So again, x1 to x2, right? Now we have tau dx phi would be the force, right, times phi. The length, the x, so it's just an integral from x1 of x2 of 1/2 tau dx phi squared dx. Right? So the Lagrangian density this system, right? L is 1/2 rho dt phi squared minus 1/2 tau dx phi squared. So it's 1/2 rho d0 phi minus v squared d1 phi squared. V is just square root of tau over rho. The tension divided by the mass density. Yeah, it's not written very well. Right? And what would be the Euler Lagrange equation? Rho, right? d0 of d0 phi minus rho v squared d1 of d1 phi is equal to 0. Right? You see that?
Yes, derivative.
So that the field phi, again, what is the field? Field describes the displacement. This is really y of x, right? It describes the displacement of the string, right? It satisfies the equation of motion of phi. Right, what do we have here? It's d0 phi over dt squared minus v squared d0 phi, v squared phi over dx squared is equal to 0. Right. What equation is that? How do we call this equation?
Wave equation?
Exactly, this is a wave equation, very good. This is a wave equation. This phase velocity, the phase is square root of tau over rho. So the Lagrangian density, right, gives us the wave equation of the field. Okay, now just a few comments. So in order to, yeah, I want to say avoid confusion, right? But enhance the confusion, It's not very custom to refer to the term Lagrangian density. Most often it will simply be called a Lagrangian, because in the framework of quantum field theory, this is the entity we work with, right? There's no real work with Lagrangian. It's just the Lagrangian density. So just terminology. Lagrangian density. Now, of course, in principle, we use the Lagrangian to get the equation of motion, right? That's the main purpose of the Lagrangian. But you know, so you can ask, why do we have to work so hard? Why simply not use Newton's law? Essentially, we get the same result, which is true. But when we look at the Lagrangians, it does help us getting a much deeper insight into problems. It's not just the equation of motion. Specifically, we will see in the Lagrangian various symmetries. And we will learn a lot about the system, even without solving the Euler Lagrange equation, or even without writing it, just by looking at the symmetries of the Lagrangian. And these symmetries, they are extremely important in quantum field theory. In fact, you know, I'm going to discuss that. I don't know if today or next week. You know, Hermann Weyl tried to write the entire physics based on symmetries, and just beautiful idea. We'll discuss that. And of course, we need the Lagrangians to derive the Feynman rules, right? Lagrangians are useful not only as a way of deriving Euler Lagrange equation, but also to see the symmetries of the problem, which are of extreme importance. Okay. Now let's start talking about Lagrangians for you know, relativistic quantum fields. So questions, by the way. I mean, this is all being done, you know, quite quickly because I want to get to here. But of course, as you can see, there's a lot of things to study here, even classically. Recommend you, you know, I don't want to give you all that as homework. I can, but not sure if it'll be that good. I trust you to, if you don't fully see that, then go and practice that a little bit yourself. If you need help from me, simply write me. I'll tell you where to look. So, okay, so we said in quantum field theory, we have multiple fields or multiple particle fields, and I'm going to write down the Lagrangian of some of the different fields that are involved. So let's start down with the relativistic scalar field. So first field we have is a scalar one. We have a spin zero scalar field. Or spin zero scalar particle is described by an excitation of the scalar field phi, right? What equation does the field phi has to satisfy? Come on, guys. see. Yeah. What equation does a spin zero scalar field has to satisfy?
Klein problem.
Very good, right? So you have to write a field which satisfies Klein-Gordon equation, right? So you have to have a Lagrangian for a free, non-interacting scalar field, which must be of the form that we can retrieve back the Klein-Gordon equation. So the way to write this field is L, the Lagrangian, LS, sorry, is 1/2 d mu phi minus 1/2 m squared phi squared. This is the Lagrangian. This Lagrangian is what we need to get back. So Lagrangian that retrieves Klein-Gordon, right? Remember d mu phi, just dt phi squared minus sum over I di phi squared, right? I is 1, 2, 3. In our convention. So what will be the partial derivatives? The L d phi. What is the L d phi? What is the L d phi? This is the Lagrangian in front of you.
Minus m squared phi.
Exactly. What is the L d 0 phi? Come on, that should be automatic.
F d1 phi.
No. Have d mu, right? So d0, d0. So the L over d0 phi, right? We just d0 phi. Because the metric, the 0, 0 component of the metric is 1, so this is also equal to d0 phi. That's because the convention of the metric we use, right? And dl over di phi. What is that? Oh, I'm sure you can do better than that.
It's minus di phi.
Yes, very good. Minus di phi, which is di phi, right? Now here we do have a minus in the metric. When in a raised index, I got this extra minus. So the Euler Lagrange equation, right? Minus m squared phi minus d0, so it's d0 squared phi minus lambda squared phi is equal to 0, which is equivalent to writing d mu phi plus m squared phi is equal to 0, which is of course a Klein-Gordon equation. For a scalar field phi. So the initial choice of the Lagrangian was a good one. Right? Now, just as a comment, which is not surprising, right? This term here, half d mu phi, this would give the the p squared term in the equation of motion, right? So this is called the kinetic term, the Lagrangian. And this second term, right, minus 1/2 m squared phi squared, this gives the mass term at the end, the equation of motion, right? So this is called, surprise, surprise, the mass term. Okay, that was the easy and simple. Questions? No. No questions, and let's move on. So the next field we learn about is the relativistic spin 1/2 field. Right? So the Dirac spinor, basically, right? So the Dirac spin, the spinor field psi satisfies Dirac equation. So we must have a Lagrangian which will give us back Dirac equation. And the Lagrangian that does that, L Dirac, psi bar I gamma mu d mu minus m psi. Actually works. So the psi, right, psi of x is the 4-component complex spinor. Right? Psi of x is a 4-component complex spinor. Of course, the same one that appears in the Dirac equation. Right. So it really has 8 independent real fields because there are 4 components. Each one is complex, so have real and imaginary parts. You really have 8 independent real fields. And we can use all these fields as generalized coordinates if we want to. But of course, it's much easier to use convenient, to use some linear combination of them. So the independent fields will take the 4 components of the spinor psi and the adjoint spinor psi bar, right? So as independent degrees of freedom, and freedom we choose sine bar. It's much more handy, right? So we must take the partial derivative with respect to each one of these, okay? You see where it comes from? And then we have dl over, okay. Let's start doing it one by one. So the partial derivatives with respect to each, it's important, each of the components of the adjoint field, so psi, adjoint spinor, psi bar, right? They would be dl over d psi bar. What is the L over d psi bar? It's just, there is left here in the Lagrangian, so just I gamma mu d mu psi minus m psi, right? And what is the L over d of d mu psi bar? What is that? What is that? Let's look at the Lagrangian. Now, guys. Become very quiet. What is the L over d mu psi bar?
Is 0.
0, right? D mu psi bar doesn't appear in the Lagrangian at all. Right? What will be the Euler Lagrange equation then?
Just minus what we have on top.
Exactly, right? Just this one equal to 0. Right? What's written here? What's written here? In the square brackets. What equation is that?
The Dirac equation.
Dirac. Thank you. This is the Dirac equation. Right? You all see that? Do you? Yeah? Question? No. Okay. Now remember, we treat psi and psi bar as independent coordinates, basically. So we have to take the partial derivative with respect to psi, right? To give us another equation. So if we take the partial derivative with respect to psi, we end at dl over the psi, right, is minus m psi bar, dl over the d mu psi. Now we have to be slightly more careful, right? If you look at the Lagrangian, we do have a d mu psi here, right? This would give us what? I psi bar gamma mu, right? We do have a d mu psi. We have an I psi bar gamma mu. The order does matter because they're not necessarily commute, which means that the Euler Lagrange equation, right, this will simply be minus m psi bar minus I d mu psi bar gamma mu. Which is, again, this is a correct equation. And it really follows from the Dirac equation, right? So again, if you look back in the Lagrangian, we have here the m minus m psi bar psi. So go down. So the minus m psi bar psi, this is the mass term. Note the similarity and the difference between this and the term in the Klein-Gordon equation. And the second term, right, the psi bar I gamma mu d mu psi, this is the kinetic term. Right. Psi bar I gamma mu d mu psi is the kinetic term. Yeah? You all with me?
Yes.
Questions? Okay, let's move on. We still have the relativistic vector field. Okay, so 3 would be the relativistic vector field. Right. So we show that the Maxwell's equations, right? Remember that when we discussed that, we have the Maxwell's equation. We express them as Maxwell's equation as d mu f mu nu equal j nu. Why? Remember that? F mu nu is just d mu a nu minus d mu a nu, and a nu is just phi. Yeah? Remember that? I hope. Somebody?
Yes.
Somebody help. Good. So the Lagrangian of the electromagnetic term would be minus 1/4 f mu nu minus j nu a mu. J mu. Sorry. J mu a mu. Right? And take the Euler Lagrange equation. What do you get back? Don't need to do the full derivation. You can tell me that without being without writing the equation. What if I do the Euler Lagrange? What am I going to get? What am I going to get if I do the Euler Lagrange?
D mu f mu nu equals j nu.
Of course. Get back Maxwell's equations. Euler Lagrange will give back Maxwell's equation. Do it at home, please, just to make sure that you're all with me. Okay. The last thing which we discussed is a massive vector field. Massive vector field. Right. So the Euler Lagrange equation, which we'll derive from the Lagrangian L Proca Lagrangian, L Proca, we did the Proca equation, right? Is minus 1/4 f mu nu and here we have a plus 1/2 m squared a mu. That's a Proca Lagrangian. And if you do the Euler Lagrange, then gives you back the Proca equation, right? Squared plus m squared a mu is equal to 0. Okay. Do it at home. Okay. Promise me? Okay. Next thing is Netter's theorem. That's kind of, I see we are sort of running out of time. The next thing I'm going to do is going to discuss symmetries of the Lagrangian. And the reason why we're so much interested in symmetries is because of this theorem following Amy Netter from roughly 100 years ago, which states that every time we have a continuous symmetry of the Lagrangian, then we have a conserved current. Okay, that is in essence Netter's theorem. Every continuous symmetry it's one M, yeah, two M's of the Lagrangian gives rise to a conserved current J mu. Right. Conserved current means that the equation of motion, right, implies that d mu J mu is equal to 0. Okay, so once we have a symmetry of the Lagrangian, we know that there is something is conserved in the system. That dates back to Amy Netter. The proof is it's not very long even. It's not very difficult, not very long, but I'm not going to give it to you right now because it will require me to define a few things which I don't want to define because it just confuses you. In any case, it can be found in any textbook of the form. It's basically in the introductory chapter to quantum field theory. It's there. You can find it in Thompson. You can find it in Peskin and Schroeder. It's slightly above what we're learning, but fine. But the proof is there, and you know it's being widely used. So let's give an example rather than proof. I'll just give an example. Right. So let's have a particle of mass m, which is orbiting in the gravitational potential of a fixed body of mass m, capital M. So consider a particle of mass m orbiting in the gravitational potential of a body, fixed body. A satellite orbiting Earth. Right? So L, T minus V, 1/2 mv squared plus gmm over r. Right? The velocity, I can split it into r and phi coordinates. So this is 1/2 m r dot squared plus 1/2 m r squared phi dot squared plus gmm over r. Right? R and phi are polar coordinates. Right? Now, is there any symmetry of the Lagrangian that you're seeing here?
There should be a symmetry in phi.
Exactly, right? The Lagrangian is independent of phi. So symmetry, that's important to look at that, right? Symmetry, the Lagrangian L is independent on phi, right? So that means that we can make an infinitesimal transformation right? Remember, it has to be a continuous symmetry. So if we take an infinitesimal transformation from phi to phi prime, which is phi plus delta phi, phi here is an angle, right? Don't confuse with a field, right? Then the Lagrangian is invariant. So infinitesimal invariant under infinitesimal transformation. Phi goes to phi prime, which phi plus delta phi. And then the corresponding Euler Lagrange equation of motion, right? Right. That means that d over dt of dl over d phi dot is equal to 0. Right, so this is the symmetry. And the equation of motion, Euler Lagrange equation, right? D over dt of dl over d phi dot equal to 0, which means that dl over d phi dot, right, which we call j, just m r squared phi dot. What is that? What quantity is that?
The angular momentum.
It's the angular momentum, right? This is a constant of motion. Right? The angular momentum. This was a simple demonstration. The idea that we have a symmetry of the Lagrangian, and that leads to a conserved quantity, which here is the angular momentum. Okay? Of the orbiting body. Now, okay, we're running out of time, so it's a good place to stop, but I will, okay, as usual, we are going slower than I was hoping to. Not sure if I'm not planning ahead properly or that I'm just too optimistic. I'll just give you a twist of what's going to happen on Tuesday. So on Tuesday, we're going to do now for the same trick, but for the Lagrangians for particle physics, right? And we're going to start with several simple symmetries. So the first will be the U1 global symmetry. We have a U1 symmetry. Going to be global. That's going to lead us to conservation of the electromagnetic charge. Right. So again, I'll take a minute just to give you a hint. So if I look at the Dirac Lagrangian, right, psi bar phi gamma mu d mu minus m psi, right, I can identify a global phase transformation here, which will leave the Lagrangian unaffected. So we have a global phase transformation. The word global is important. Global phase transformation. Meaning that psi of x goes to psi prime of x, which is e I q chi psi of x. This is a unitary matrix. It's a 1-by-1 matrix really. So it's a u of chi psi. There is no real need to divide it's a unitary matrix, so I don't have to write it as E times Q times chi. I can simply write it as E times I chi or something like that. The reason why I put the Q here is because it's going to get the physical meaning. Right? The physical meaning is going to be the charge. Chi is some parameter, Q is just the real constant of the model, right? Which seems to be unnecessary. But when I make this transformation, so this is a transformation that I can make. When I make this transformation, and I look at the Lagrangian, right? So L Dirac, psi bar, I gamma mu d mu minus m psi, right? Transform would be psi bar u star, right? Hermitian conjugate, I gamma mu d mu minus m u psi. And u being unitary matrix can simply go through the unitary constant matrix. It's simply going to go through the d mu because it's global symmetry. So this is just going to be equal to LD. Okay. And this is the continuous transformation. And so Netter's theorem will tell us that there is some conserved current. And as I'm going to show you, it's going to take about 10-15 minutes. The conserved current is going to be the same current we already saw. The same electromagnetic current we already saw. That's why I told you that Q is going to get the interpretation of the electric charge. But I think I'm going to do that properly on Tuesday. All right. Questions? No questions?
תודה רבה, שבת שלום.
Shabbat shalom. Have a great weekend. As you know, on Sunday, we're going back to quarantine. Hopefully, it's not going to affect us. We'll simply continue to do the Zoom meetings and the Zoom lectures as usual. I do want to ask you, I'm unhappy with the quietness. If this is about the time now to go and refresh your memory, make sure that everything is clear in your mind. We still have time. The examination period is still far. But we're getting there. In a few weeks' time, the semester will be over. And so now is the time to make sure that you don't have any, gaps in your knowledge. And if there is anything, please do not hesitate. It's a very small class. So feel free to ask me. And if I don't answer right away, as you saw, I'm checking out and I come back to you later on. Or simply send me an email if you prefer, my email. And that's it. Wish you good luck and a good weekend.
Thank you, you too.
Okay, so we can stop sharing and stop the recording.